This is lecture 7 for composite materials, and we will be talking about the different uh, polymer composite processing methodologies that have not been discussed so far. So, the first one we will talk about is pultrusion. Pultrusion is basically taking the fibers and the resin system and extruding it through a die into a particular shape. So it's an automated process for manufacturing composite materials into continuous cross-section profiles. And it can usually be grouped into two categories. That is, if you want solid rod and bar stock, or if you have structural profiles, like if you want something with a hollow stock and things like that, or if you want something that is you need to produce in large volumes, pultrusion would be a good method to adopt. It is not exactly based on price competitiveness, but it is based on characteristics or mechanical properties and structural properties that are not found in traditional materials. For example, if you want a ladder rail, it is the highest volume application, or if you have something in the electric utility industry, insulators, hotline maintenance tools, and I think even the um, product for the tie rods used in the transportation, I mean, not transportation, the rail industry. Uh, it could be it could be used for that. And the types of fibers used mostly are E glass and S glass, and carbon and graphite are mostly used only when the cost uh, is going to be of the volume. I mean, that can justify the volume that you want to get, and you can get multiple types of fiber forms. It can be rowing, mat, and fabric. Um, the resin systems, the basic requirement is that they have to be low viscosity, and it should be able to cure quickly, because as soon as it comes out, within a few minutes it should cure. And so you would use polyester, that is most common, or vinyl ester or epoxy. But if it is epoxy, then the processing speed is much low and the reaction rate is very slow. So it has to be matching the exotherm that should be contained within the die. And you have to use typically a very short pot life if it is epoxy. And the temperature profiles are typically hotter. So there is a tendency for these materials, especially if they are epoxy based, to bond strongly to the die wall. So typically that is not, I mean, unless your processing is that well defined and that well controlled, you probably don't want to use epoxy for pultrusion. But it is still used. So there are 6 key elements in the pultrusion process, where 3 of them occur prior to the machine and 3 of them are integral to the pultrusion machine. The first one is that you need to be able to handle the reinforcement in a proper manner. You need to have a resin impregnation station, and you need to have a material forming area. And the those that are attached to the machine are uh, components that heat and consolidate, and then you need to have something to pull the material out of the die, and you also need to have something that will cut the pultruded samples with a straight edge. That means your cutting machine has to be extremely strong and extremely sharp. So these are some pictures of some pultrusion equipment parts. You can have multiple things like, fishing rods, window frames, arrows, etc. So the handling system is mainly to handle creels that are continuous fiber creels that are first um, placed on a process line, and then it is followed by creels designed for rolls of matte fabric and or veil. And as soon as it enters, or as it is close to the entry point of the die, the fibers have to be extremely well aligned. Suppose, I mean, these are moving at extremely fast speeds. So just imagine, I mean, this is coming like a bullet, and you have to be able to control that, and you have to be able to align the fibers such that the properties are going to be consistent from part to part. Most of the time you have a dip bath. So these are the fibers, or the creels are passed over and under bars, and that will cause the fiber bundles to spread, and it will enter the fabric well. So you need to have products that, typically products that are rowing construction, that can easily be formed from a resulting flat ply, is what you would typically choose. And the resin baths can be custom made, because when it is sometimes impractical to dip the materials into the bath, that is, if the creels are vertical, that means you have to have a custom resin bath. Or you may have walls and plates that are machined and positioned to accommodate the necessary preformed shape. And you need to be able to impregnate the creel without moving those reinforcements outside their intended forming path. So typically the forming will follow the impregnation. So you have different dies or holes and clearances that must be designed. So first of all, you need to have the proper tension with which you are pulling it. Second of all, you need to be able to make sure that the resin is not splaying all over the place and making a whole mess. Um, and if you have a hollow part, that means you have a mandrel that is cantilevered through the pultrusion die. That means you typically can't have um, a closed end with a straight um, kind of a tool at the edge. So you need to have the mandrel that might be having a draft angle to it. I hope you understand what I mean by draft angle. So it's a sloping angle. It might only be 1 or 2 degrees. So it is very easy, after the part is made, it is very easy for you to pull out your mandrel and create the part. You can also have different kinds of impregnating and forming method, where you inject the resin directly into the die after the dry materials are formed, which will typically eliminate the problems associated with dip bath limitations. So you don't make a whole mess out of your shop floor. uh, and you can also get, sometimes you will get satisfactory wet out, and you may be able to avoid the air entrapment. And sometimes you want to have 60-65% volume solids loading or fiber loading, so you may not be able to do that in the dip bath type of a situation. So you can avoid that by having this kind of a resin impregnation method. And then the next step is consolidating and curing. So you have to position and anchor the die, and it needs to apply the right kind of pressure. And sometimes you also need to be able to cool the die, uh, and you may want to shut down the die, shut down the heating at a particular point so that when the part is coming out, it is at the right temperature and curing profile. There are three common curing methods. One is curing in the die itself, or after the part comes out, you have a curing by it going through a tunnel oven, or um, you may bring out the part from the pultrusion die and you split the mold halves, and then the line stops while it is curing, and then it is continuous when the curing is complete. So you can have non-uniform cross section if that is needed. So the most important condition in the pultrusion process is the die heating profile, because it determines your rate of reaction and determines the position of the reaction within the die, when it starts and when it stops, and it also controls your magnitude of peak exotherm, because if you do not control the curing process, then it will exhibit poor physical and mechanical properties, and it may look okay, but the properties will be pretty bad. So you want to control this, which is the most critical pultrusion process control parameter. Then you need to be able to clamp it and pull the material. So sometimes it may come out 10 feet or more by the time you allow the pulling device to pull it out. So I don't know if you have ever seen the process by which you extrude or you um, hard work or cold work uh, a steel rod or a steel wire. So this is something very similar, except that this is a composite. So you can have different ways to do this. You can have intermittent, or you can have continuous pull or continuous belt pullers. So you don't need to remember all these things, but just understand that this is a process by which you create the final part. And then the final thing is to have some way to cut off the sample so that you have consistent cross section and consistent length. And these cutting tools are typically continuous grit carbide or diamond edge blade. The main advantage of pultrusion is that you can produce large volumes in um, in large volumes is the basic benefit, and then you can prevent process waste, because most of the time the part is net, and you can use a wide variety of reinforcement types, forms, and styles, and you can create thin wall shapes, very typical of, very similar to extruded aluminum, PVC pipes, and things like that. And you can also fabricate extremely large parts and extremely long parts. And these are typically transportable. So, if you want to make large volumes and large sizes, pultrusion is a good process to have. But the difficulty is that the cross sections must generally be uniform, and it is very difficult to maintain tight tolerances because the shrinkage is typically 2 to 3%, which is difficult to control. And you can also have issues with maintaining the straightness along the length, and you can have issues with having a complex curing profile. You may not be able to do that. So you have to have resins that cure with single profiles, or maybe maximum 2 or 3 profiles, 2 or 3 steps. So that completes the pultrusion, and now we come to filament winding. Filament winding is typically used for large parts, and you need to have an inside mandrel that can be removed. And you need to be able to, I mean, it's very similar to pultrusion in that, except that it is wound around a mantle. So you need to have a fiber delivery system, and it is the fibers are delivered at speeds, and the mantle is continuously rotating, say on a lathe type of a machine, and it will control the winding angle and the placements of the reinforcement. And successive layers are added at the same or different winding angles until finished thickness is reached. So typically it has to be a surface of revolution like a cylinder pipe or tubing, or spherical or conical, or sometimes you may also have rectangular or square shaped. Typically pressure vessels or storage tanks, and in which case you need to have enclosures attached to the mantle. And after the curing is over, the end fittings become part of the part, and you need to be able to uh, remove the inside mantle. So again, similar to pultrusion, you can have fiber in roving form or fiber in prepreg or toe form. And the rowing yield will affect the processing. So higher yield rowing facilitates wetting, but more layers are required to meet specified thickness. So it can introduce longer winding times, and you can also have different resin systems. So the fiber could be in the form of a prepreg where the resin has already been introduced, or you may have a wetting bath or a resin bath for epoxy, vinyl ester, polyester, BMI, etc. And which means that viscosity and pot life are extremely major processing considerations, and low viscosity is very critical for complete wetting, and suitable viscosities are between 350 to 1000 centipoise at room temperature. Sometimes you may also heat it up slightly in order to improve the wetting. So but if you heat it up, then it can reduce the pot life. You can also have what are called polar winding machines. So in which case the mantle is typically in the vertical position. So it will eliminate the deflection due to weight, and you can wind zero degree layers. And the control is much easier, and but it is limited to prepreg because wet winding system is difficult to control, because what happens is that if you have wet winding, the resin can just flow down and make a mess of the shop floor. So typically these winding machines have multiple axes of rotation. So typical and the lowest cost ones are four axis winding machines. So you have uh, the X and Y, and in this direction, and sometimes the winding head can also rotate in multiple directions. So that will, or this will be another control. So these are the different winding parameters that winding axis that you can control the actual component itself. The mandrel can be of many different kinds. The most common one is a segmented collapsible metal. So if it is segmented, that means after you make the part has to be chopped off and you have to be able to remove the mantle. That means after you make the part, you have to weld it back together, which means you are reducing or introducing extremely bad points of failure for the components. Or you may have eutectic salt, which means, I mean, that is also another big problem, because these eutectic salts have to be heated up to about 350 degrees centigrade and or 500 degrees centigrade. and then you have to make it into a mold, and after that you have to be able to wind the part around it, and the eutectic salts are soluble in water, but the washout material is not is hazardous, even though it is salt based. So you can't throw it into the landfill, or you cannot throw it uh, into your sink. It has to be disposed of as hazardous material. um, you can also have plaster, or you can have sand, and or you can have inflatables, and now you also have water soluble tooling materials, which I was part of when we developed it about 10-15 years ago. So these are the, so again, similar to the pultrusion system, you have the fiber delivery system. You have tension devices, because the fibers have to be wound at a particular speed and tension, so that the final part is not going to have any kind of defect in it, or voids in it. And similar to pultrusion, you also have impregnation tanks, and when it comes out you have pins that will spread out the fibers and make sure that the resin has penetrated the fibers well. And then you also have a doctor blade to remove the excess resin. Otherwise, after the part is made, it will spill all over the place and make a mess of the shop floor. So you have multiple strands, multiple spokes that will divide the strands that are coming out from the fiber creel. And then it goes and winds on top of the mandrel. And then after that, you also have the deposition head, which is a flat rolling band, and then it can swivel freely as the feed direction is reversed, and the feed head is controlled in path tangent to the mandrel. So that means when it is winding, there are no gaps between the mandrel and the feed head. So this is the feed head, so it makes sure that the fiber stays on top of the mandrel and there is no gap between the mandrel and the fibers. So what are the advantages of filament winding? It is highly reproducible. You can have very large shapes. I'll show you some parts that have been made using this process. For example, tanks that are used for some of our missile systems, or some of the space systems that need to carry a lot of fuel. Some of the hazardous fuel, hydrazine and things like that, are carried in these kinds of tanks. And now the big push is to have these tanks carry high pressure compressed natural gas, low pressure natural gas, or cryogenic natural gas, or cryogenic fuels. And the other advantage is that the process can be automated, which results in cost savings. What are the disadvantages is that the part configuration must facilitate mandrel extraction. So typically if you have trap tooling, it is extremely difficult. And the mandrel could be complex and expensive, and if it is a one-piece, one-time use mandrel, that means if it breaks for any reason, you have to start all over again. So a lot of cost can go into this process. And sometimes you also have the external surface may not be satisfactory for some applications. So you have to go back and put some kind of a coating on top of that to give it a nice smooth surface finish. So this one shows a contemporary application. So if you go and um, I mean, if you have it in the um, display mode, you should be able to double click on that, or you might be able to go in and see, Google that, you will be able to find this contemporary application. So let me stop here and I will start in the next set of slides.